Radyo, Teleradyo Marcelo. Sa gitna ng mapanubok na panahon, magkahatid sa kakibat ay diskusyon. Sama-sama tayo, kahit magkalayo. Sa programang ito, tiyak ang pagkatuto. Teleradyo, Teleradyo Marcelo. Teleradyo, Teleradyo Marcelo. Teleradyo, Teleradyo Marcelo.
Magandang araw, Delphilarians! Sa taong po ito, pag-iiwan natin ang isang radyo. Mabuhay ang kinematics.
Radyo is always at your service. Kaya naman, ang feedback mo, suggestions nyo ay mahalaga sa amin to improve our programs on air and online. Para alam ni teacher yung strengths as well as the things in your mind na mas makatutulong sa mas effective na pagkatuto sa teleradyo. Please take time to send your feedbacks via Teleradyo Mu, which you can access by scanning the QR code on the right or typing the URL provided here, bit.ly/3ORVAY9. One more, this time you follow. bit.ly/3ORVAY9.
Makinig, manood, nasa teleradyo. Makinig, manood, nasa teleradyo. Teleradyo, Teleradyo Marcelo. Sa gitna ng mapanubok na panahon, magkahatid sa kakibat ay diskusyon. Sama-sama tayo, kahit magkalayo. Sa programang ito, tiyak ang pagkatuto. Teleradyo, Teleradyo Marcelo. Teleradyo, Teleradyo Marcelo. Teleradyo, Teleradyo Marcelo.
What a blessed afternoon, everyone. Hello, I am Engineer Roelay Demdem, or you can simply call me Irat, still your physical science teacher for another episode today, here live at Radyo Marcelo, ang telearalan ng bawat Maloleño. I am equally excited for this topic of physical science and all the online interaction we can possibly create through this live teleradyo. But before we proceed with anything else, I would like to acknowledge our secondary school principal for Dr. Maria Victoria C. Vigo, my master teachers, Ma'am Rosita A. Alopre and Sir Bartolome R. Asa, the science area, and all the senior and junior faculty members. Magandang hapon po sa ating lahat, mga ma'am, sirs. And of course, to all the students who are tuning in with us here at Teleradyo Marcelo, I highly recommend to comment your name, grade, and section on our chat box to acknowledge your presence and of course your answers to our activities and assessment for today. Okay, so before we officially start our lesson for today, I want you to think of this question. What do you think will happen when we drop a feather in a cannonball? Will they hit the ground at the same instant? One light object and one heavy object. To answer your question whether their rates of fall were the same or different, let me present to you our objectives for today. Okay, at the end of this session, you should be able to first compare and contrast the Aristotelian and Galilean concepts of vertical motion, horizontal motion, and projectile motion. Second is to explain how Galileo inferred the objects in volume fall with uniform acceleration and that force is not necessary to sustain horizontal motion. And finally, to explain the subtle distinction between Newton's law of motion or the law of inertia and Galileo's assertion that force is not necessary to sustain horizontal motion. Okay, so now before we actually go to these topics, I am calling for a review of our past lessons. I only want to know if you really understood and if you can still recall the previous topic. Okay, so this review will really test your comprehension and memory as well. Okay, for the first review question. Okay, which of the observations below was used by Aristotle to prove his claim that Earth is not flat? Letter A, he noticed that all things seem to be moving around the Earth except for Earth itself. B, he argued that since the shape of the moon appears to be round, then the Earth must also be round. C, he argued that lunar eclipse only happens when a round, opaque object blocks the passage of sunlight. D, he noticed that during a lunar eclipse, the shadow cast by Earth on the moon is round. Okay, put your answers down below and I will be reading it based on what will actually appear on my screen. Again, the first review question is, which of the observations below was used by Aristotle to prove his claim that Earth is not flat? A, he noticed that all things seem to be moving around the Earth except for Earth itself. B, he argued that since the shape of the moon appears to be round, then the Earth must also be round. C, he argued that lunar eclipse only happens when a round opaque object blocks the passage of sunlight. Or D, he noticed that during a lunar eclipse, the shadow cast by Earth on the moon is round. Okay. So I recognize some answers as some say that the answer is letter D. So it's actually correct. He noticed that during a lunar eclipse, the shadow cast by Earth on the moon is round. Okay, next question. We have which of the statements below refers to the information gathered by Eratosthenes about a phenomenon that happened at the same day and time during the summer solstice in Syene and Alexandria. A, in Syene, sunlight shines directly down a deep well and is reflected back, while in Alexandria, the vertical pillar did not cast a shadow at all. B, in Syene, the vertical pillar casts a shadow, while in Alexandria, sunlight shines directly down a deep well and is reflected back. C, in Syene, sunlight shines directly down a deep well and is reflected back, while in Alexandria, the vertical pillar casts a shadow. Or D, both in Syene and Alexandria, that the structures cast a shadow? Okay, the correct answer is letter C. Okay, let's continue with the next question. Which of the following is also presented by the Greeks to prove that the Earth is spherical? A. Solar eclipse. B. Sunrise and sunset. C. Ships sailing seem to be gradually disappearing in the horizon. Or D. Passing of the comet in Earth's orbit. Okay, which of the following is also presented by the Greeks to prove that the Earth is spherical? A. Solar eclipse. B. Sunrise and sunset. C. Ships sailing seem to be gradually disappearing in the horizon. Or D. Passing of the comet in Earth's orbit. Okay, the right answer is letter C. Okay, for the next question, aside from Aristotle, who among the philosophers below believed that the Earth is spherical? Letter A, Pythagoras and Mesopotamians. B, Pythagoras and Plato. C, Plato and the Mesopotamians. Or D, Mesopotamians and Egyptians. Okay, aside from Aristotle, who among the philosophers below believed that the Earth is spherical? A, Pythagoras and Mesopotamians. B, Pythagoras and Plato. C. Plato and the Mesopotamians, or letter D, Mesopotamians and the Egyptians. Okay, the right answer is letter B. Okay, so let's move to the next question. Based on Eratosthenes' calculation, the circumference of the Earth is equivalent to letter A, 250,000 stadia. B, 50,000 or 5,000 stadia. C, 2,500,000 stadia, or letter D, 500,000 stadia. Okay, the correct answer is letter A, 250,000 stadia. Okay, number 6. Which phase of the moon is shown in the figure? Letter A, full moon. B, new moon. C, first quarter moon. Or D, last quarter moon. Which phase of the moon is shown in the figure? A, full moon. B, new moon. C, first quarter moon. Or D, last quarter moon. Okay, the correct answer is letter C, first quarter moon. Okay, for number 7, the following are astronomical phenomena that were already observed by the ancient people even before the telescope was invented, except for letter A, solar eclipse. B, phases of the moon. C, craters of the moon. Or letter D, planet like Venus. The following are astronomical phenomena that were already observed by the ancient people even before the telescope was invented, except for blank. Letter A, solar eclipse. B, phases of the moon. C, craters of the moon. Or letter D, planet like Venus. And yes, the correct answer is letter C, craters of the moon. Okay, number 8. Which of the statement below describes a lunar eclipse? A lunar eclipse occurs when the Earth is behind the Sun and the Moon is in front of the Sun. B, a lunar eclipse occurs when the Moon is between the Earth and the Sun. Letter C, a lunar eclipse occurs when the Moon is forming 90-degree angle with the Earth. Or letter D, a lunar eclipse occurs when the Earth is between the Moon and the Sun. Okay, the correct answer is letter D. A lunar eclipse occurs when the Earth is between the Moon and the Sun. Okay, for the last two questions, based on the observation made by the ancient astronomers, the Sun rises in the blank and it sets in the blank direction. Letter A, west-east. B, southwest. C, north-south. Or D, east and west. Okay, the correct answer is letter D, east and west. Okay, for the last question, Okay. Refer to the figure below, phases of the moon. Which among the numbered figure represents the full moon? Is it letter A, 1, B, 2, C, 3, or D, 4? Okay, the correct answer is letter A, 1. Okay, I think we had that enough for review, so we can now finally move on to our today's topic. But before we proceed to our lesson, I want to thank your participation in this activity. So now for our today's lessons, we have the laws of physics. So it is Aristotle versus Galileo. So describing the motion. Okay. For Aristotle, he said that every object has a proper place in the universe. So it's the natural motion and the violent motion. While Galileo says that an object can move freely in the absence of friction. So describing the motion, we can actually say that there is a motion if letter A, or number 1, if there is a change of position. Letter B is if there is a passage of time. And C, describe using a referent or reference point that is not moving. And letter D, if there is a change of position relative to some reference point over a defined period of time. So if you notice some kind of this phenomenon, then we can say, or we can tell that there is a motion. So speed. So speed is how much the position has changed or the displacement, and or what period of time is involved. Speed is also the quotient of distance and time. So constant speed is moving equal distances in equal time periods, and while average speed is average over all speeds including increases and decreases in speed. And instantaneous speed is a speed at any given instant. So considers a very short time period. So the formula for speed is equal to the quotient of distance and time. So speed is defined as the ratio of the displacement or distance or the distance covered in straight line motion for the time elapsed during the change. This ratio is the same as the found by the calculating the slope when time is placed on the x-axis. So the answer is the same as shown on this graph because both the speed and the slope are ratios of distance per unit of time. Thus, you can find the speed by calculating the slope from the straight line or picture of how fast distance changes with time. So as you can observe, this is a graph of distance versus time. So as time goes by, the distance covered also increases. So it's linear or positive slope. So in the next slide, you can also notice that at 1 hour, we have covered the distance of 50 miles. Then after another hour, we are now at the 100 miles from our initial position. And after an hour again, we are at 150 miles from our initial position. So the total elapsed time is 3 hours. So if you know the value of any of two of these three variables of distance, time, and speed, you can actually find the third. So what is the average speed of this car? So the average speed is known as or defined as the final displacement minus initial displacement all over the final time minus the initial time. So if we are going to compute the average speed for this situation, we will have 150 miles or 150 miles minus 0 mile all over 3 hour minus 0. So we actually have 50 miles per hour as our average speed for this situation. Okay, velocity. Now, what is velocity? Velocity is a vector quantity. It describes both direction and speed. So it's a quantity without direction is called a scalar quantity. So speed is analogous to velocity. However, velocity has a direction. So that's their difference. Okay, so velocity is also the vector that we can represent graphically with arrows. Here are three different velocities represented by three different arrows. So the length of each arrow is proportional to the speed, and the arrowhead shows the direction of travel. And lastly, we have the acceleration. So three ways to change motion. We can change the speed or change the direction or change both speed and direction at the same time. So a change of velocity over a period of time is defined as the acceleration. So it's the rate. So acceleration is equal to change of velocity all over time. So four different ways of acceleration. This is a sample of a car that is actually accelerating. So first we have a constant direction, increase speed. Next we have constant direction, decrease speed. And we have change direction, constant speed. Letter D, we have the change direction, change speed. So Aristotle theory of motion. Aristotle thought that there were two spheres in which the universe was contained, the sphere of change and the sphere of perfection. So the earth was seen to be a perfect sphere. The earth was fixed in place and everything else in the universe revolved around the earth. So one of the Aristotle's proof that the earth is a sphere, Aristotle argued that falling body moved toward the center of the earth. Only if the earth is a sphere can that motion always be straight downward, perpendicular to the earth's surface. Another of Aristotle's proof that the earth is a sphere, the earth shadow on the moon during lunar eclipse is always round. So if the earth were a flat cylinder, there would be some eclipses in which the earth would cast a flat shadow on the moon. So the shape of a sphere represented an early Greek idea of perfection. Aristotle's grand theory of the universe was made up of spheres, which explained the natural motion of objects. So natural motion. Aristotle was the first to think quantitatively about the speeds involved in these movements. He made two quantitative assertions about how things fall. The natural motion. Heavier things fall faster, the speed being proportional to the weight. So the speed of fall of a given object depends inversely on the density of the medium it is falling through. So for example, the same body will fall twice as fast through a medium of half the density. So notice that these rules have a certain elegance, an appealing quantitative simplicity. So if you drop a stone and a piece of paper, it's clear that the heavier thing does fall faster, and the stone falling through the water is definitely slowed down by the water. So the rules at first appear plausible. The surprising thing is, in view of Aristotle's painstaking observations of so many things, he didn't check out these rules in any serious way. It would not have taken long to find out if half a brick fell at half the speed of a whole brick. For example, obviously this was not something he considered important. From the second assertion above, he concluded that a vacuum cannot exist because if it did, since it has zero density, all bodies would fall through it at infinite speed, which is clearly nonsense. So the force motion. For force motion, Aristotle stated that the speed of the moving object was in direct proportion to the applied force. So Aristotle called force motion violent motion. This means first that if you stop pushing, the object stops moving. So this certainly sounds like a reasonable rule for, say, pushing a box of books across a carpet, or the Grecian ox dragging a plow through a field. So this intuitively appealing picture, however, fails to take account of the large frictional force between the box and the carpet. So if you put the box on a sled and push it across ice, it wouldn't stop when you stop pushing. Galileo then realized the importance of friction in these situations. So it would appear as true as though Aristotle's theory of motion was correct, as objects do tend to stop moving when the force is removed. Aristotle taught that the natural tendency of objects was to be at rest. Objects remained at rest until a force acted on it to make it move. So Aristotle and Galileo differed in how they viewed motion. Again, Aristotle thought that the natural tendency of object was to be at rest. Galileo, however, thought that it was every bit as natural for an object to be in motion. Okay, inertia. Galileo explained the behavior of matter to stay in motion by inertia. Inertia is the tendency of an object to remain in motion in the absence of an unbalanced force such as friction and gravity. So Galileo challenged the Aristotelian view of motion and focused on the concepts of distance, time, velocity, and acceleration. So we have falling objects here. Okay, the velocity of an object does not depend on its mass. Differences in the velocity of an object are related to the air resistance. In the absence of air resistance, a vacuum, all objects fall at the same velocity. This is free fall, which neglects air resistance and considers only the force of gravity on the object. Okay, we have here Galileo versus Aristotle's natural motion. Galileo observed that the velocity of an object in free fall increased with the time the object was in free fall. From this, he reasoned out that the velocity would have to be proportional to the time of the fall and proportional to the distance of the fall. So according to a widespread story, Galileo dropped two objects with different weights from the Leaning Tower of Pisa in Italy. They were supposed to have hit the ground at about the same time, but discrediting Aristotle's view that the speed during the fall is proportional to the weight. Okay, so Galileo knew that from his reasoning that a free falling object should cover the distance proportional to the square of the time of the fall. He also knew that the velocity increased at a constant rate. And then, he knew that a free falling object accelerated toward the surface of the Earth. Galileo then concluded that objects persist in their state of motion in the absence of an unbalanced force, a property of matter that we know inertia. Thus, an object moving through space without any opposing friction continues in a straight line path at a constant speed. So the application of an unbalanced force in the direction of the change, as shown in the figure, is needed to slow down, speed up, or change the direction of travel. Okay, so now we have the acceleration due to gravity. Objects fall to the Earth with uniformly accelerated motion caused by the force of gravity. All objects experience this constant acceleration, and this constant acceleration is 9.8 meter per second squared, or 32 feet per second squared for each second of fall. This acceleration of 9.8 meter per second squared is the acceleration due to the force of gravity and is given the symbol lowercase g. So an object dropped from a tall building covers increasing distances with every successive second of falling. So the distance covered is proportional to the square of the time falling. Okay, so the velocity of a falling object increases at a constant rate, 32 feet per second squared if we will going to use the English system of measure. But if we have the international system of measure, we have 9.8 meter per second squared. Okay, so moving objects before Galileo, Aristotle's views dominated in this scene. Aristotle's world is based on empirical observations. Okay, so drop two objects at the same time, both fairly heavy, so that air resistance can be neglected. Aristotle says that the heavier object should reach the ground long before the lighter one. Actually, they hit at about the same time. Okay, prepare two identical metal spheres. Cut one in half, drop the two halves and the whole sphere at the same time. They will also reach the ground at the same time. So there are several differences between Galileo and Aristotle. Galileo analyzes simple problems such as ship moving, while Galileo, like Aristotle, observes reality. So however Galileo makes experiments to prove his conjectures, Aristotle jumps from observations to conclusions, but he does not perform tests to prove or disprove his ideas. So the key idea is that the reality is very complicated, and we have to work on simple systems to understand how things work. And we need to confront our ideas to reality to make sure we did not come up with some fantasies. Okay, so to simply wrap up all this experimental science regarding Galileo and Galilei, okay, so physicists observe the phenomena of nature and try to find patterns that relate this phenomena. These patterns are called physical theories, or when they are very well established and widely used, physical laws or principles. But please remember that calling an idea a theory does not mean that it is a random thought or an unproven concept. Rather, a theory is an explanation of natural phenomena based on observation and accepted fundamental principles. So an example is the well-established theory of biological evolution, which is the result of extensive research and observation by generations of biologists. So to develop a physical theory, a physicist has to learn to ask appropriate questions, design experiments to try to answer the questions, and draw appropriate conclusions from the results. So as we discussed a while ago, legend has it that Galileo Galilei dropped light and heavy objects from the top of the Leaning Tower of Pisa in Italy to find out whether their rates of fall were the same or different. So from examining the results of his experiments, which were actually much more sophisticated than in the legend, he made the inductive leap to the principle or theory that the acceleration of a falling body is independent of its weight. So the development of physical theories such as Galileo's often takes an indirect path with blind alleys, wrong guesses, and the discarding of unsuccessful theories in favor of promising ones. But physics is not simply a collection of facts and principles, it is also the process by which we arrive at general principles that describe how the physical universe behaves. No theory is ever regarded as the final or ultimate truth. The possibility always exists. Those new observations will require that a theory be revised or discarded. So it is in the nature of physical theory that we can disprove a theory by finding behavior that is inconsistent with it. But we can never prove that a theory is always correct. So getting back to Galileo, suppose we drop a feather in the cannonball. They certainly do not fall at the same rate. This does not mean that Galileo was wrong. It only means that this theory was incomplete. If we drop the feather and cannonball in a vacuum to eliminate the effects of the air, then they do fall at the same rate. Galileo's theory has a range of validity. It applies only to objects for which the force exerted by the air, due to air resistance and buoyancy, is much less than the weight. Objects like feathers or parachutes are clearly outside this range. So often a new development in physics extend a principal range of validity, and then Galileo's analysis of physical bodies was greatly extended half a century later by Newton's law of motion and law of gravitation. That is why Galileo is known as the father of kinematics. He also studied pendulum motion by observing the swinging of the chandelier in the adjacent cathedral. So now to elaborate kinematics of mechanics, we have rectilinear motion, horizontal motion or vertical motion or free-falling bodies. Okay? So to actually show to you the three kinematics equation. Okay. So the three kinematic equation we have here, the displacement. So displacement and distance are analogous. We have here the speed or the velocity. And of course, we have the acceleration. Acceleration, when we have a vertical motion, is regarded as the gravity. And gravity is 9.8 meter per second squared if we are talking about the Earth gravity. Okay, so the three kinematic equation, we have the final velocity is equal to the initial velocity plus or minus the acceleration times time. We also have the square of the final velocity is equal to the square of the initial velocity plus or minus 2 acceleration times the distance or displacement. And finally, we also have the displacement is equal to initial velocity times time plus or minus 1/2 times acceleration and then time squared. Okay, so these are the three kinematic equations that Galileo Galilei has invented. Okay, so we know that if we are going to find the derivative of displacement, we are going to have the value of its velocity. And if we get the uh, derivative of the velocity, then we will arrive to the acceleration. And if we get the integral of acceleration, we will have the velocity. And if we get the integral of the velocity, and then we have the displacement. So this concept actually works more in the field of physics or the specialization. And if we are going to have our free falling bodies, it's also the same. Okay, it's also the same formula. The only difference is that the displacement here would be represented as h. For example, we have h as height is equal to the initial velocity times time plus or minus 1/2, and then gravity times t squared. So the a would be interchanged as g, and the s would be interchanged as h. And then now we have the horizontal and vertical motion, or the rectilinear motion, and the free falling bodies. Okay. Okay, so now we have the final part of our session, the assessment. Okay, so that's the end of our lesson for this session. So if you have any question, do not hesitate to comment it below. But if all things were clear, let's find out by answering the assessment 1 to 10. Okay, so be ready with this activity. I will present to you each question. Just simply comment your answer down below. Okay, so for the first question. Okay, number 1. What is the straight line motion caused by the gravitational pull of the Earth? Letter A, free fall motion. Letter B, horizontal motion. Letter C, projectile motion. Or D, none of these. Okay, so that is right. The correct answer is letter A, the free fall motion, or the free falling bodies. Okay, for number 2. Okay, how does the acceleration of a stone thrown upward compare to the one thrown downward? Letter A, greater. B, smaller. C, the same. Or D, undetermined. Okay, again, how does the acceleration of a stone thrown upward compare to the one thrown downward? Letter A, greater. B, smaller. C, the same. Or D, undetermined. Okay, the correct answer is letter C, smaller, of course. Okay, next question. What will happen to a moving object if no external forces act on it? Letter A, it will come to an abrupt halt. B, it will continue moving at the same speed. C, it will move slower gradually until it stops. Or D, none of these. Okay, the correct answer is letter B. It will continue moving at the same speed. For number 4, when no forces act on moving objects on air, how can you describe their paths? Letter A, circles. B, ellipses. C, parabola. Or D, straight line. Again, when no forces act on moving objects on air, how can you describe their path? Letter A, circles. B, ellipses. C, parabola. Or D, straight line. Okay, the correct answer is letter D, straight line. Okay, for the question number 5, suppose you are riding a motorcycle but it runs out of fuel while driving. The engine stops abruptly, but why don't you? Letter A, because of gravity. Letter B, because of inertia. Letter C, because of continuation principle. Or letter D, because of resistance. Okay, so for the right answer for this item is letter B because of the inertia. Okay. For number 6. Suppose you are standing in the aisle of a moving bus. If the driver suddenly makes a left turn, why are you likely to lurch to the right? Because of blank. Letter A, an equilibrium challenge. Letter B, an unbalanced force. Letter C, your momentum. Or D, your tendency to keep moving forward. Okay, the correct answer is letter D, your tendency to keep moving forward. Okay, for number 7, which of the following best describes an accelerating object? Letter A, object at rest. B, object in mechanical equilibrium. C, object moving at a constant velocity. D, object moving slower. Okay, the right answer for this item is letter D, object moving slower. Okay, for number 8, a ball rolling along a horizontal surface maintains a constant speed. Why is it so? Letter A, friction is present. B, no inertia on the object. C, no horizontal force acts on it. Or D, surface is smooth. Again, a ball rolling along a horizontal surface maintains a constant speed. Why is it so? A, friction is present. B, no inertia on the object. C, no horizontal force acts on it. Or D, surface is smooth. Okay, very good. So the right answer is letter D, surface is smooth. Okay, for number 9, why do a coconut and a bird's feather falling from a tree gain speed as they hit the ground? Letter A, their velocity changes. B, there is a gravitational force acting on them. C, their inertia. Or D, their nature to become closer to the earth. Again, why do a coconut and a bird's feather falling from a tree gain speed as they hit the ground? Letter A, their velocity changes. B, there is a gravitational force acting on them. C, their inertia. Or letter D, their nature to become closer to the earth. Okay, very good again. So the correct answer is letter B. There is a gravitational force acting on them. Okay, for the final question, we have here which of the following is true about acceleration due to gravity. Letter A, it is different for different objects in free fall. B, it is a fundamental property. C, it increases in decreasing altitude. Or D, it is a universal constant. Okay, again, which of the following is true about acceleration due to gravity? Letter A, it is different for different objects in free fall. B, it is a fundamental property. C, it increases in decreasing altitude. Or letter D, it is a universal constant. Okay, the right answer is letter D. It is a universal constant. Okay, so thank you, Del Palarians. I am seeing a lot of comments in here. Thank you for your actively participating in our session for today. So if you have any questions, please do not hesitate to personally message me or any physical science teacher we have here in Marcelo. And if you don't have any questions, I also would like to introduce to you the members of the production team. So yours truly, Ma'am Joy Presimay Bulaong and Ma'am Josephine M. Nicolas. Okay, so that's the end of our session. So don't forget to like, share, subscribe to Teleradyo Marcelo in its YouTube channel and Facebook page. See you next session. God bless everyone. Stay safe and healthy.
Teleradyo is always at your service. Kaya naman, ang feedback mo, suggestions nyo ay mahalaga sa amin to improve our programs on air and online. Para alam ni teacher yung strengths as well as the things in your mind na mas makatutulong sa mas effective na pagkatuto sa Teleradyo. Please take time to send your feedbacks via Teleradyo Mu, which you can access by scanning the QR code on the right or typing the URL provided here, bit.ly/3ORVAY9. One more, this time you follow. bit.ly/3ORVAY9. Kaya send your hashtag TBH o hashtag RT dito sa Teleradyo Mu kung saan ang feedback mo, suggestions nyo ay mahalaga sa Teleradyo.
Magandang araw, Delphilorians!
Sa taong po ito, na pagdiriwang natin ang isang daan